You spend all afternoon building it, but eventually the ocean returns. The tide creeps in, and your sandcastle dissolves back into the beach. In school, we learn a simple explanation for this daily rhythm. The moon's gravity pulls the ocean's water directly toward it, piling it up on the coast. But if the moon is pulling water to one side of the Earth, we should only see one bulge. Instead, at the exact moment the tide is high on the side facing the moon, it is also high on the side facing deep space. Most textbook diagrams gloss over this second bulge. To understand how the ocean actually moves, we have to look past the idea that water is simply being lifted upward. We need to stop looking at the beach and zoom out to view the entire Earth-Moon system as a single, interacting physical unit. Gravity follows a strict rule of distance. Its strength drops off rapidly the further you get from the source, a phenomenon known as differential gravity. Viewed from above, the ocean facing the moon is closest, experiencing the strongest gravitational pull. This intense attraction draws water outward, creating our first tidal bulge. But the solid Earth's center is further away, feeling a slightly weaker gravitational tug than the surface. The first high tide is a direct result of that extreme proximity. But because this gravitational tug weakens across the diameter of the planet, the rest of the Earth is about to experience something much more counterintuitive by centrifugal force, flinging water outward as Earth spins. That isn't actually what's happening. Consider the geometry of the system. The solid rock of the Earth is physically closer to the moon than the ocean sitting on the far side. Because differential gravity pulls harder on closer objects, the moon pulls the solid Earth away from the distant far side water. Like pulling forward inside a loose sweater, the fabric at your back doesn't stretch, it stays put. The far side water is simply left behind. The second high tide occurs because the planet is literally pulled out from under the water. Earth's own downward gravity is about 10 million times stronger than the moon's outward tug. Physically, the moon does not have nearly enough strength to literally lift billions of gallons of water vertically into the sky. This map shows the moon's true influence, the tractive force. Instead of lifting water vertically, the moon's gravity pushes horizontally across the Earth. Acting like giant hands pressing the planet's poles, they squeeze the ocean sideways, pulling them into two high tide bulges. High tides aren't the result of a vertical lift from space, but a global horizontal squeeze across the planet's surface. These two massive water bulges stay relatively stationary, locked into place by the moon's gravitational grip. As the Earth spins, its coastlines rotate right through these stationary bulges. Your local beach isn't watching the water rise and fall, it is physically rotating into deep water twice a day. But the moon is also moving along its orbit. By the time the Earth completes a 24-hour spin, the moon has shifted ahead. The Earth has to rotate for an extra 50 minutes every day just to catch back up to the bulge. This daily game of catch-up is why high tide arrives roughly an hour later every single day. The sun also contributes to this pressure. Despite its massive size, its distance is so vast that its tidal squeeze is less than half as strong as the moon's. When the sun and moon line up, their forces combine for massive spring tides. When they sit at right angles, they fight each other, resulting in much weaker neap tides. As the ocean foam slides up the sand, you are witnessing the endpoint of a massive physical chain reaction. A wave washing over a sandcastle is actually visible evidence of a global squeeze orchestrated across hundreds of thousands of miles of space.